Thanks. Man, I'm glad that worked. I was having computer problems earlier. Um, Thanks for the invite. It's really great to be able to talk to this group. And I want to share kind of a quick run through of a sprawling project that's been going on for a couple of years. It has multiple people involved. Ko Cheng Tang was a key person. He's moved back to Wuhan University, but he was at NCAR. Mojgan, Naoki, are here with me at NCAR. And then Chanel and Chris and Marquetta and Brantley all work for the Corps of Engineers and Reclamation. So those are the two major federal water agencies. And we've also had support for this project from NOAA as well as NASA. And then the computing is done at NCAR, which is where I'm working right now, part-time. I also work at the Colorado School of Mines. Anyway, this is kind of a co-development effort. It relates to creating a new CMIP 6 based update for of data sets that are used in US-wide hydroclimate planning and guidance and research and analyses. And this is an activity that's been going on for, I guess, 15 years or more, where we try to produce these US-wide data sets for both climate, downscaled from the various CMIP scenario MIPS that come out every 5 years or so, and then also for hydrology, including stream flow and other fields like snow and soil moisture. And then these get used in agency reports and water security studies, as well as by researchers. We've tried to follow a very process modeling based chain, basically starting with these climate model scenarios, downscaling them for the most part statistically, running them through hydrology models and coming up with outcomes that can be used by the water agencies. So I'm going to give an update. We're basically trying to update all the components of this process. I'm not going to talk much about all of it, but I do want to talk about the hydrology modeling. So basically, when we go to do this, some of the major challenges and choices we have to make are what model to use and how to implement it across the domain. In the past, on a model called VIC, and in early studies that used a very coarse grain kind of gridded approach. Another huge challenge that's actually been a real Achilles heel of these studies is the need to try to calibrate these models across an entire country, which is quite large and is heavily managed. So it's something that we really struggle with, particularly when we try to use complex process models. So in the past, we've ended up with sort of patchwork efforts to calibrate parts of the domain, and then some parts are left completely uncalibrated, just lack of time and maybe the available data. Another big aspect of this is determining meteorological forcings for these models and putting through high quality surface precipitation and data sets, both for the calibration of the models and also for the training of the statistically downscaled data sets. In the past, some of the data sets that have been used have had some real severe artifacts due to interpolation when you look at things like trends and precipitation and temperature. So lastly, the downscaling approach is always a huge question. I'll touch on that just a little bit as we go forward. So how are we working to improve these different components? Well, one thing, so I mentioned prior agency efforts have used a lot of research grade data sets, such as Maurer and Livna at coarse degree resolutions, 8th degree, 16th degree. We've been building out an entirely new station data set. It spans about 74 years, going back to 1950, where we've brought together multiple networks to get up to high station counts across for precipitation and temperature. And then we use kind of a spatial regression machine learning approach that's contained in this package called GPEP that we produced for this project in part, that can actually produce ensemble surface forcing analyses, so we are able to estimate the uncertainty in the forcing. So that's been a huge effort. We do have this data set that we're now using. For the hydrology modeling, we are using a model called SUMA now. It's really a framework that gives you a lot of flexibility over specifying different process parameterizations. I've been using this model for about 10 years. And one of the things I really like about it is its flexibility to represent water or land surface in different ways, and also the separation of the numerical solver from the parameterizations, the flux parameters, so that it becomes a very accurate simulation, and we can do a lot of things with load balancing and parallelization. And this has also been supported by these water agencies over the years. So I'll say more about that. The domain that I'm simulating on is catchment based. So basically, it's about 100,000 mesoscale catchments across the US, based on the USGS HUC 12 delineation. And then we use a Merit Hydro for channel routing. And you can see that we have to include basins both in Canada and Mexico because they drain into the US water sheds. For routing, we use a kind of multi-method routing model called Misoroute. It's a hydrologic routing, it's not hydraulic routing. And we use a diffusive wave approach. We implement this on this Merit Hydro channel network, which is about 200,000 reaches across the US. And so it supports some water management, but for the most part, we're simulating natural flow as we calibrate and go to project future climate impacts. Another huge part of the effort that's been hand in hand with the water agencies is to search for naturalized stream flow estimates that we can use on the main stems of rivers that are managed to validate the modeling. And this was an effort where we sent out a request to basically all the operational, regional, and local offices of these two agencies that manage the water in the US to send back their inputs on the process. It took probably a year. Really built out an extensive stream gauging network combining both natural and managed locations that we can use, but that using their naturalized flow that we can use for calibration and validation. The biggest challenge in all of this, I'm just going to check the time. Biggest challenge in all of this is really how do we get these models calibrated? And as I mentioned, that's been a longstanding kind of Achilles heel of the whole process. We've had really unsatisfactory outcomes when we have delivered data sets in the past that start to get used in planning and in various local areas, and only to discover that the various features of the hydrographs are not calibrated, such as peak flows or seasonal volumes and timing. As hydrologists, we know how to calibrate watershed models in specific locations where we have enough data, packages out there with different algorithms for optimizing. But this isn't really that scalable to apply to a large domain. Even if we go one by one across the whole country, and calibrate several thousand basins, we still have to regionalize them across the domain. So as we've seen, that doesn't work very well with traditional methods. One thing that's come out of the machine learning community in recent years is that if you use deep learning models, you can calibrate across all basins at once, and you end up getting better results from learning from this hydrologically diverse data set for all the individual locations. This has never really worked with process modeling in the past. When we try to lump them all together and train on them, we end up getting sort of less satisfactory results than training individually. So that's why the blue lines are to the left on the process models part, and then to the right on the deep learning model part. So where the scores are best to the right. So for this project, we basically took this machine learning strategy of jointly training over large numbers, over 1,000 basins at once. But because it's so difficult to run these complex hydrology and land models, over that we use a machine learning emulator. So we basically train the emulator to learn the relationship between the basin geoattributes, the model, so the objective functions that we care about for the calibration, and the model parameter sets. And then we wrap that into an iterative optimization so that we can then learn from all the basins at once. And not only that, the trained emulator at the end of it ends up giving us a basis for regionalization. We can use in an optimization to search in any arbitrary location for good parameter sets. And we've tended to find that this works pretty well. This is just a quick example to show, sorry, looking at the clock again, to show some results. We're training over here the camels data set and seeing that if we start with a priori simulation time series in green, we can greatly improve them over this training data set. And in general, the emulator is able to derive its estimates of high performing parameter sets from sort of initial random sampling in blue down toward lower errors as it goes through each successive iteration. And the kind of performance we've gotten, we just had this paper come out 2 days ago, actually, from this approach of kind of integrating these process models with AI-based techniques for training large domain models. These results have been really encouraging. I think they're starting to be comparable to what we see from the simple conceptual models that we know calibrate well. We still are working on the regionalization aspect and testing how well that works this month, and hope to kind of check that box as we go into the next month and start running the future climate runs. I just want to say something about this talk is really not about the downscaling of the climate. This part has been really strongly specified by the agencies who have also supported and funded the production of data sets using a method called LOCA2, which has been used to downscale hundreds of scenarios from CMIP 6. And at NCAR, we have projects where across a whole range of different statistical downscaling data sets, and also, I guess these are all statistical in this plot, but from sort of deep learning to other more traditional statistical ones. And of those, we find LOCA2 performs fine. And in any case, we're not going to do something different than the agencies are asking for. So I won't go more into this aspect, but we are penciling out doing all these or downscaling and running all these LOCA2 scenarios. For right now, there is a bit of work in planning how this is going to be implemented on high performance computing. So let's sort of pencil out the computational costs that we need to support, maybe around 22 million core hours for the runs and about 120 terabytes of storage as we output stream flow from the models. We're looking at, soil water, snow water equivalent, aquifer storage, and some other kind of water balance variables. Now so we're in the process right now of basically finalizing the full domain hydrology model and getting ready to kick off all these downscale climate runs with the hopes of producing these data sets for the Corps and Reclamation within the next couple months. I want to say a little bit about why it's nice to work with these agencies. They have their own internal planning and guidance and policy documents and objectives that are kind of driving us on deciding how to use this data set and what products to produce from it. For instance, in the Corps of Engineers, they have guidance for incorporating impacts for inland hydrology and civil works designs and projects. So it's very targeted what we're doing. It's not just kind of generating a data set. And for instance, in a place like the like Pacific Northwest. And I think one of the people who works with me, Naoki Mizukami, is going to give a more detailed talk on this project, which is related to this one in a couple months, I think in November, for this same webinar series. So sort of a prompt for that. But anyway, these agencies are doing their own internal vulnerability studies to try to look at different objectives of their management systems, such as flood risk, fish flows, recreation, refill for water supply, and tying those to specific outcomes that we can simulate. And then these with our hydroclimate and climate analyses and data sets, so they're able to tie the hydrologic metrics that we might produce from all this modeling to metrics of performance of the reservoir system that really affect their management objectives. And so once they've done that, they can then go and use this large ensemble of projected stream flows and other hydrologic and climate variables to kind of track how vulnerabilities may change in the future. So they use like a rolling window approach over 30 years and go out and look at the kind of probability that different ensemble members are going to trigger vulnerabilities going into the future. So there's quite a sophisticated kind of partnership in generating all these data sets that are targeted toward these kinds of planning and management policy uses. So in summary, um, this research is part of a multi-year effort that's sponsored by multiple agencies to develop the CMIP 6 informed future downscale climate and hydrology data sets for these applications. And I should say that once these data sets hit the street and the models and the methods papers, it also gets wrapped up into new research. So it's not just purely applied work. And we've really benefited from the guidance and review of the agency team members. It's not a project where you write a report at the end of each year. It's more that we meet, every 2 weeks to a month and review the progress on different components and get inputs on how to what's acceptable and how to change direction if we need to. So this fall we should be finished generating all these ensemble of 1850 to 2100 hydrologic scenarios for use by the agency. So I think I'll leave it with that, and thank you for your attention. Welcome any questions.
Thank you, Andy. Has anyone got any questions they'd like to ask? I've got one I would ask straight away. This is a huge amount of work that's obviously been done to generate this data set. So is it going to be publicly available globally, or is it just in the US?
For this particular set of projects, it will all be the US. And as the papers come out, we're starting to also stage the data sets in our new research data set archive. I'm forgetting the name of it. It's like the NCAR DEX or something. But yeah, certainly the techniques can be applied globally, but those have to come under other projects and partnerships, I think.
Okay, thank you very much.